Okay, let me read this question. This says, a small disc and a thin uniform rod of length L, whose mass is eta times greater than the mass of disc, lie on a smooth horizontal plane. So let us say there is a smooth horizontal plane, and over this there is a rod that is kept, and rod of length L, and the mass of this rod is, let us say, eta times m, and there is a disc, and this is frictionless, so this surface is mu is equals to 0. The disc is set in motion in a horizontal direction and perpendicular to the rod with velocity v, after which it elastically collides with the end of the rod. So there is a disc that is set into motion this side with velocity v. The mass of this disc is m, and this makes an angle 90 degree. So this velocity is perpendicular to the velocity of rod. Are you getting? This collides with one end of the ball, so let us call this end as A, this end B. So this disc collides with end A. Find the velocity of disc and the angular velocity of rod after the collision. So two things we have to find. Velocity of disc, this first thing, and this is omega of rod, angular velocity of rod. There are two things that we have to find. What is the angular velocity of rod and what is the velocity of disc after the collision. So let us discuss. I think all of you have copied this one. If I look from the top, the same diagram will look something like this. There is a rod that is kept, and there is a ball that is coming on this line. As you can say, disc that is coming on this line. Initially this is coming with velocity v that is given in the problem. This is kept at rest. Mass of this is m. The mass of this is eta times v, eta times m. Are you getting? This is coming with velocity v. This is kept on a horizontal plane, and the collision is given elastic. So we have an elastic collision. So we'll also write one equation using elastic collision. Now let us say this is the initial situation. After collision, what will happen? This rod, as soon as there is a collision, let me draw another diagram for after the collision. So this is before collision. This is before collision. Let us draw another diagram after collision. So after collision, just after collision, let us say this ball is going away, returned with velocity u. This rod, now it will have two kind of tendencies. So there is a torque acting here. So this rod will start rotating. So let us say this rod will start rotating with angular velocity omega. This rod will also move. So let us call this velocity is by which the center of mass is moving. Let us call this is a BCM. So this rod is basically two kind of motion. Translational motion, in that case center of mass is moving with velocity BCM. This rod is also rotating. So let us say rotational angular velocity is omega. Now I have to write three equations because we have three unknown u, v, u, BCM and omega. You see, there is no force is acting in the horizontal direction, while internal force, this rod and this ball collide, so this force is internal in nature. So I can write one equation from momentum conservation. So let us write equation from momentum conservation. No force is acting, so in horizontal direction, momentum has to be conserved. So if I do momentum conservation, I can write one equation. Initial momentum is in this direction. Let us say this direction is positive direction. So for me, let us say this direction is positive direction. So m into v, that is the initial momentum in this direction you will have. And what is the final momentum in this direction? The mass of the rod is eta times m, and the velocity of rod is bcm. This is the momentum of rod. minus, because this is moving in this direction, so minus m into u. So this is one equation. Second equation I will give from collision is elastic. So collision is elastic. So I will get the second equation from elastic collision. And that is velocity of approach is equals to velocity of separation. So velocity with a sign, velocity of approach is equals to velocity of separation. This I am going to apply. So let us see, if you see this point and this, what is the velocity approach? So velocity of approach is v, because this is in the rest. So velocity of approach is v. What is the velocity of separation? If you see this point will have two velocities. So what is the total velocity of this point? So this point will have a velocity bcm due to the translation, and L by 2. So let us say rod has a length L. So this is L by 2 into omega. So this is L by 2 into omega. So what is the velocity of this point? That is bcm plus L by 2 into omega. Are you getting? So I can write bcm plus L by 2 into omega. This is the velocity this side and this is the velocity this side. So we have to add these two velocity plus u. That's the velocity of separation. Are you getting? You see, this is the velocity of separation, this is the velocity of approach. Because this is going this side, this is going this side, so we have to basically add these two velocity. So let us say this is equation 2. Now also in this whole system total torque is also 0. You see, in this system the total torque that is acting about point, this point, middle point, total torque, there is no torque acting. So you see, this applies a force this side, this also. So internal torques, these are the internal torque. This is hitting this rod this side and this rod is hitting this side. So these are the internal torque. There is no external torque. So this means angular momentum has to be conserved. So angular momentum is also conserved. So system will have angular momentum that is conserved. So I can write the third equation from angular momentum conservation. So let us try to write the angular momentum conservation equation. If you write angular momentum conservation, you have, so what is the initial angular momentum? So this I am doing with the midpoint. So this is angular momentum conservation I am writing about the midpoint of rod. So this I am writing about midpoint of rod. Are you getting? So this I am doing with midpoint of rod. So what is the initial angular momentum about midpoint of rod? So if you see this, are you getting or not? Now this is coming with velocity v, so you will have mv, that is the mv into distance this L by 2. Are you getting? And this angular momentum in this direction. So initial angular momentum will be mv into L by 2. Now see, this angular momentum is in this direction. A final angular momentum I have to write. Now the rod will have angular momentum about this point. This rod about this point is only rotating, so I into omega. And I is ml square by 12, m is eta m. So let me write m ml square by 12 I into omega. This is the angular momentum. This is again this side in this direction. But now this ball that is moving in this direction, so this will also have angular momentum mvr, so m into u into L by 2, but this is going this side, so this will have this direction. So I will have plus m u L by 2, but this will have in this direction. Are you getting? So now if I plug the sign, let us say this is a positive, this is a positive, so this will become negative. So if you cancel m, you will have v into L by 2, this is equals to eta L square by 12 into omega minus ul by 2. If you do some more manipulation for this equation, you will have, let us cancel this, v is equals to, so 2 will be multiplied and L will also multiply. So you will have, let us multiply by 12, so you will have 6v. This is equals to L goes out, so you will have eta L omega minus 6u. Are you getting? So this is the third equation you have. Now we have three equations, 3 unknown. Now it's one equation solving. So we have to find u and omega. Are you getting? I think all of you have written the top equations. So let me again copy the first equation. The first equation is, after cancelling the m, you will have v is equals to, this is basically VCM. Let me see, there is a, so what is the VCM and what is the V? Yeah, there is some mistake, I think. No, it's right. Okay, let us write the first equation. So you see the first equation is this one. B is equals to mm cancels out, so we will have V is equals to eta times VCM minus u. So let us plug this equation here. B is equals to eta times VCM minus u. So this is my equation number 1. You can write equation number 2 also. So equation number 2 is B is equals to VCM plus L by 2 omega plus u. Now you have to find for u, v and omega. So what can I do? Basically v is known. That the initial velocity is given to you. And what are the unknown we have? Omega, u and VCM. These are the 3 unknown we have. So these are unknown. So let us try to solve for omega, u and VCM. So what can we do is, let us plug the value of VCM in equation 2. Okay, let us plug the value of VCM in equation 2. So from equation 2 we will have V is equals to VCM, and VCM is nothing but u plus v by eta. So this is u plus v by eta plus L by 2 into omega plus u. Are you getting? Now you see the equation number 1, that is 6v, this is equals to eta L omega minus 6u. Now what you do is, you multiply this equation by 6 and add. So if I multiply the above equation by 6, this will be something like this, and then if I add these two equations, so 6u goes out, so you will have 6v plus 6v, 12v. This is equals to, you will have u remains here. I cannot, okay, this will not work because there is a u, so leave this one. Think yourself, how can I solve this one? So let me think. What we will do is, let us write this equation again. So we have v is equals to u plus v by eta plus L by 2 into omega. The same equation I am copying before multiplying by 6 u, and the lower equation you have 6v is equals to eta L omega minus 6u. So this is the lower equation. If I multiply this above equation by eta, you will have eta v is equals to u plus v plus eta L omega by 2 also plus eta u. Now if I multiply by 2, so you will have 2 eta v, this is equals to 2u plus 2v plus eta L omega plus 2 eta u. Are you getting? Now this equation, now I can use this equation 6v is equals to eta L omega minus 6u. Now I can subtract these two equations. So this is minus, this is minus, this is plus. So this term goes. So you will have, this side you will have 2 eta v minus 6v, 2 eta v minus 6v, this is equals to 2u plus 6u, that is at u, plus 2v and plus 2 eta u, this is 2 eta u plus u term I have written, so 6 plus 2 at eta u, now only v, so plus 2v. So v go this side, so we will have minus 8v, so 2 eta v minus 8v, this is equals to If I take 2u common, so I will have eta plus 4. Now if I do more mathematics, I can take 2v common here also. So 2v, if I take common, eta minus 4, this will be 2u eta plus 4. So 2 goes out, so you will have u is equals to, u is given, no, u is not given, u is equals to eta minus 4 divided by eta plus 4 into v. So this is the velocity of rod, end point velocity of ball. So this is the velocity of ball, or you can say velocity of disc. Have you copied the upper or not? Let us copy again, and then we'll go for this one. So let us copy this one first. This is simply mathematics, solving equations. Now you can solve yourself for omega. So this is your task. You solve for omega, and this comes out to be, if you solve omega, should I solve or you can solve? Okay, let me solve. So you have the second equation, that is 6b is equals to eta L omega minus 6u. So 6u will be 6 times u, I know, eta minus 4 divided by eta plus 4 into b. So this comes this side, so I can take 6b common. So this will be 1 plus eta minus 4 divided by eta plus 4 is equals to 6L omega, eta L omega. So now eta plus 4, eta minus 4, so we will have 2 eta on the top. So 6v, 2 eta divided by eta plus 4 is equals to eta L omega. So eta goes out, so we will have 12v, and this is 4 plus eta. So we will have 12v on the top. I think you are able to see 12v divided by 4 plus eta. This is equals to omega L. So omega will be 12 by 4 plus eta into v by L. Now the question says, at what value of eta velocity of this after the collision will be equal to 0. So what will be the value of eta for which velocity of ball, that is u, after collision is 0. And this is possible for eta minus, so this is the velocity, u is equals to eta minus 4 divided, so this will be 0 only if eta is equals to 4. So one part of the question says when u will be 0, that is possible only if eta is equals to 4. Now the second part of question says what will be the value of eta so that if direction reverses. So direction of the ball should reverse. What will be the velocity of eta? Now you see, we have already considered the case in which the direction of velocity of ball has reversed. So initially this is going in this direction. Now u is my in this direction, that is the reverse velocity. So only thing is, if this number comes out to be positive, now my direction is reversed. So eta minus 4 should be greater than 0 because this is the only term that is can be negative. So if I have eta minus 4 that is greater than 0, in that case velocity gets reversed. So eta should be greater than 4, that is the end of condition. To velocity should be reversed. So this is the condition for velocity of ball or disc. Velocity of disc gets reversed. Are you getting or not? So you see, this is a quite good problem. We have applied 3 conservation laws: momentum, angular momentum, and energy conservation. You see, we have not written the energy conservation. We have written velocity of approach is equals to velocity of separation. And this equation is very important. Either you write energy, since the collision is elastic, you can write energy conservation, or you can also write velocity of approach is equals to velocity of separation. Somebody wants, you can write the energy conservation, but the energy conservation equation will not going to give you more information. It will give you the same information. So this means If you want to use the energy conservation, either you can write energy conservation or you can write this expression. So if somebody says collision is elastic, you have two options. Either you can write velocity of approach is equals to velocity of separation, or you can write energy is conserved, that is energy initial is equals to energy final. Both are going to give you the same equation. So you does not think that you are writing this equation and you are writing energy conservation equation, you will get two different equations. No, at all. You will get the same equation. So these are the same equation you will get at the end. So you are getting either, you have to write either energy conservation or velocity of approach is equals to velocity of separation. Generally, velocity of approach is equals to velocity of separation term does not contain any square, and that's why handling this equation is very easy. So whenever we have elastic collision, try to write velocity of approach is equals to velocity of separation in place of writing energy conservation equation. That will always make your calculation simpler. Now the second important point we have in this question is momentum conservation. Because there is no forces that is acting, so momentum will be conserved. Initially, the momentum is m into u, m into v, or finally you can write the momentum. Another important point you have, finding the velocity of this point. When you are writing velocity of approach equals to velocity of separation, this point will have two kind of velocity due to the center of mass movement, due to rotation, so Vcm plus L by 2 into omega. So this is the total velocity we'll have. So, and angular momentum conservation you can write, you have to look for the, since I am conserving the angular momentum about this point, initial angular momentum is simply mvr, but after this collision, angular momentum will be, after this is rotating, so I into omega plus this ball is going this side, so mvr of the ball, that will also there. So I have to write angular momentum of system, not only for rod. I have to write angular momentum for rod as well as for ball, because this both contains in my system. And rest of the part of the question is simply mathematics. Once you have written the three equations, rest of the part is simply mathematics. And u comes out to be, so question also asks when the velocity of the ball, or that is the velocity after collision of the ball, will get 0. That will happen if eta is equals to 4. So you can remember, if a rod of mass 4m and a ball of mass m colliding elastically, with the one end, the ball will come into the rest. This result you can remember. Are you getting or not? If the rod is of 4m mass, ball is of m mass, they are colliding elastically, kept on a horizontal table. Ball after the collision will come into the rest. Somebody can ask this question in objective type of question. Basically, this is not objective. If you have done this problem, then you can remember the result easily, because this result is very easy. One can remember, and if you have 4 choices, you can always remember this result comes out to be when eta was 4, because you have done this problem. Okay, now, and velocity gets reversed. This is possible only if eta is greater than 4. This is very logical. If the rod that is very high mass, the mass of the rod is very, very high, in that case there is a chance that ball can reverse back. But if the rod is not very highly massive, in that case rod cannot deflect the ball in opposite direction. So rod will move as well as ball will move in the same direction. Are you getting? We'll discuss the next problem.